Hello, my name is Maddison Tollett, and today I will be presenting my senior capstone research proposal, the inhibition of genetic variants of CYP1A2 with ciprofloxacin and structural analogs. My inspiration for this proposal comes from the research that I had anticipated on conducting prior to the pandemic, where I planned to investigate the impacts of genetic variation on the effectiveness of a potential smoking cessation agent. I was initially drawn to my original project out of fascination for this idea of developing a drug therapy by inhibiting a drug metabolizing enzyme, and I knew I wanted to carry on that theme into my research proposal. So with that in mind, I began to think about common addictions that are lacking pharmacological treatment, and I started to consider looking at a substance that I use nearly every day: caffeine. Caffeine is the most widely used psychostimulant in the world, and in America, 90% of adults use caffeine daily. While there are significant health benefits to caffeine consumption, there are also several health risks, which include increased blood pressure, increased risk of certain forms of cancers, increased risk of certain forms of diseases, and sleep disturbances. Many users who try to stop experience a variety of withdrawal symptoms, which include migraines, fatigue, anxiety, irritability, depression, and difficulty concentrating. Recently, the DSM-5 designated caffeine withdrawal as a formal disorder, acknowledging the merit of the condition and recognizing the potential of clinically significant problems related to caffeine use. However, unlike many other conditions such as alcohol withdrawal and nicotine withdrawal, there are no pharmacological treatments available for caffeine withdrawal today. So this made me think that inhibiting a caffeine metabolizing enzyme could work to aid caffeine addiction cessation. So I started to look into the pathways and enzymes which metabolize caffeine, and pictured is an overview of those pathways. I found that 95% of caffeine is metabolized in the liver by an enzyme called cytochrome P451A2, which is abbreviated as CYP1A2. Because this enzyme is so highly involved in caffeine metabolism, it has the potential to be a good target enzyme for inhibition. So to provide some background on how cytochrome P450s work, here is an overview of a typical cytochrome P450 reaction cycle. These enzymes constitute a major family of heme protein enzymes which catalyze the monooxygenation of a wide variety of substrates. The reaction cycle begins when a substrate binds close to the heme in this little pocket, causing a conformational change in protein structure. This conformational change in protein structure allows for the transfer of the first electrons from NADPH-bound cytochrome P450 reductase, which is basically a protein that delivers electrons. This reduces the heme, and molecular oxygen is then able to bind, and the second electron is then transferred over, and the molecular oxygen is activated by this transfer of the second electron, and the molecule is cleaved. So at the end of the cycle, you have one oxygen atom left inserted into your substrate and one oxygen atom leaving in the form of water. After determining that CYP1A2 is a potential target enzyme for my research project, I began to look into its known inhibitors. Research has shown that fluoroquinolones, an important category of antibiotics that are generally safe and well tolerated, inhibit CYP1A2 to varying degrees. These antibiotic drugs are typically used to treat infections of the urinary tract. Ciprofloxacin specifically is a known moderately potent mechanism-based irreversible inhibitor of CYP1A2. An irreversible inhibitor is advantageous because it binds to the enzyme so that no other enzyme substrate complexes can form. And in comparison to reversible inhibitors, this provides a prolonged decrease in caffeine metabolism, since it would require the CYP1A2 enzyme to be regenerated. This type of inhibitor would allow for a convenient dose rate and lower dosing. Norfloxacin and ofloxacin are also known to inhibit CYP1A2 to varying degrees, but there is a limited amount of research out there on these two compounds. So all this background leads to my hypothesis that ciprofloxacin and structural analogs could be effective agents to help caffeine addiction cessation. The proposed study has two specific aims. First, to determine the effectiveness of ciprofloxacin and ciprofloxacin analogs to inhibit caffeine metabolism in wild-type CYP1A2. And second, to determine how CYP1A2 genetic variability impacts the inhibition potency and mechanism of ciprofloxacin and structurally related analogs. Human CYP1A2 displays a wide range of genetic variability, and there's evidence that this genetic variability impacts the rate at which caffeine is metabolized. However, it is unclear how this variability influences the inhibition potency and effectiveness of ciprofloxacin and other fluoroquinolone inhibitors. So 4 of the most common variant alleles will be constructed using standard molecular biology techniques, and these alleles will be expressed in E. coli, purified, and the variation in binding affinity and inhibition potency will be assessed via ligand binding titrations and spectral enzyme activity assays, which I will explain in a moment. So the expression and purification. The construction of the variant alleles will be performed prior to this using standard molecular biology techniques, and the variant enzymes will then be expressed in E. coli. So the spread plate of E. coli will be made and allowed to grow. And then a broth culture with a colony will be inoculated and allowed to grow, and IPTG and thymine will be added, and these compounds act as signals for the bacteria to start growing even more. And we will allow this to sit and express for 48 hours. Then centrifugation will be implemented to harvest the cells, and we're going to lyse these cells by osmotic shock and sonication, which basically means that we're going to break open the bacterial cells using sound waves. And finally, to obtain protein of high purity and high P450 content, we're going to use Ni2+ affinity chromatography and cation exchange chromatography. Chromatography techniques work and purify the protein by taking advantage of the difference in physical properties. So, in order to measure the ability of potential inhibitors to bind the enzyme, we will use a ligand binding titration. And so this works because the heme right here, which is the dark blue molecule, can exist in 2 different states. These 2 different states have different properties, and they absorb at different wavelengths. The substrate-free P450 heme is found to have an absorbance at 420 nanometers. And then when the substrate binds to the heme, the molecule undergoes that same conformational change in protein structure. And the heme is found to have an absorbance around 390. Therefore, the binding of the substrate is identified by a reduction in the absorption band at 420 nanometers and a resulting increase in the absorption band at 390 nanometers. And this is plotted on the different spectra. So established methods will be used to conduct this spectral ligand binding titration. Solutions of CYP1A2 are titrated with the ligand and monitored via absorption spectroscopy. The different spectra will be collected, and the change in absorbance will be plotted against the ligand concentrations, from which dissociation constants and binding affinity can be measured. This procedure will be repeated for each inhibitor and with each of the genetic variants. So after conducting the ligand binding titrations, we will have an idea of how well the inhibitors are binding the enzyme. And the next step is to see how well these potential inhibitors are actually working to inhibit enzyme activity. 7-ethoxy resoruven is a marker for CYP1A2 activity. And in order to measure the activity of CYP1A2, we can measure the amount of product or resoruven that is formed when you incubate CYP1A2 and ethoxy resoruven. So we can do this through fluorescence spectroscopy because resoruven fluoresces at a different wavelength than 7-ethoxy resoruven. First, the substrates will be added, and the next step is to add the enzyme system and incubate. Finally, the reaction will be quenched with trichloric acetic acid, and the fluorescence spectroscopy will be performed to quantify the product. This procedure will be repeated in the presence of inhibitors, and the results will be compared to determine the effectiveness of inhibition. This will also be repeated for each of the CYP1A2 enzyme variants to assess the impacts of genetic variation on this inhibition. So overall, I'm hopeful that these studies will contribute to the development of novel caffeine addiction cessation agents and contribute to just further understanding of the effects of genetic differences on CYP1A2 mechanism and CYP1A2 inhibition. I would like to wrap up this presentation by thanking Dr. Chan for all of her help and guidance throughout this past year. And I would also like to thank the chemistry department as a whole for all their help and support throughout my time at Pacific. I would also like to thank my mom for coming during her work. Thank you, Amy.